It may be kind of small today. It may be kind of small today because I'm giving a test that's lasting until 8 o'clock. So we'll see what happens. How you doing all? Did you survive the nomenclature quiz? Christina, you look like you're barely surviving here.
I am, and I'm trying to cook dinner at the same time.
Oh, good for you. What are we having tonight?
It was chicken with spinach, tomatoes, artichoke, feta. Good stuff.
Better than what I'm having. I'm having leftover chili.
Yeah, see, we had that last night.
Good.
The nomenclature lab was really helpful for the exam, by the way.
I thought it would be, you know.
Yeah, thank you.
Well, it's not, don't thank me.
Yeah.
Dr. Musgrave did that thing over and over again. And that's one of the things that, literally speaking, you're not going to do it unless you're forced to do it. And once you're forced to do it, you do well on the exam. What can I tell you?
Yeah, it worked out.
Yeah, good enough. Congratulations. I'm glad you did well. How'd you do on it, Christina?
So far, besides the last question, I think I had a 79.
Out of 125?
Yeah.
That's fine.
Well, no, 79%. I don't remember what the.
Okay. 79% out of 125.
Sure. I don't know. My head's spun from it. You know?
Was it fair?
Yes.
Okay.
I studied most of the day too.
Good. That's all I can ask. If it's a fair test, that's all I can ask, you know? Anyway, Marie, did you get my email back or did you email me, Marie?
Yes, I saw your email. Thank you. I was in a hurry. That's why I didn't pay attention. That's why.
Yeah, basically that happens on occasion.
Yeah.
Okay.
Mhm.
It was 98, by the way, Professor. 98. What was it? Yeah, 98 out of 125.
I already figured it out for you. 15 more points. If you get everything on that last question, you're really pushing an A.
I hope so. I don't want to take the final.
The final's easy. If you've got a degree in chemistry. Anybody else? It's Mila. How'd you do on it, Mila? Okay. I got 12 people in here, guys. Are we ready to start to get this over with?
Yes.
Okay. All right. We're going to watch Christina as she cooks dinner. It is a chicken with spinach fettuccine. Christina?
Yeah, something like that. A bunch of stuff put in a pan. It's getting ready to go in the oven.
Okay, guys, are we seeing the screen now? Did I share it or not?
Not yet.
Not yet.
How about now?
Yeah.
Okay.
Yes.
You see, that's why I have you here. If I didn't have you here, I would be totally lost. Okay, we're dealing, unfortunately, guys, this is, for those of you that just took the test, unfortunately, this would have helped. I'm sorry about it. It's just the way things worked. I wanted to get the second test before you have break. So I apologize for those of you that are in my lecture. Okay. All right. I've got to get you to understand the differences between observations and conclusions. And basically, what you use to detect changes are your senses. You're seeing, you're making observations, but you're not just observing with your eyes. You're observing with your nose, you're smelling. If something different smells, then maybe your chemical has maybe your chemicals change properties, and if it's changed properties, it probably is something new. If you feel something, if something starts to get hot, that might indicate that it's releasing energy and we have a chemical change going on. If you are hearing something, if you get a loud bang, or you can hear fizzing going on, you've got some sort of a change going on. Property change, we probably have chemical changes. Now, that's our observations. Our observations are what we're seeing. And the strategy we're using in this laboratory, we're going to look at the things before you mix them. And you're going to make observations of the things before you mix them. Then you're going to mix them. And you're going to make observations after they've been mixed. If you get some sort of a physical change, then it's possible that you have a new chemical. If you've got a new chemical, then you have a chemical change, a reaction did take place. Does that kind of make sense, guys? That's the overall strategy. A conclusion basically is going to be something that you determine based upon your observations. Okay, I see gas bubbles floating up. Something's changed. My conclusion is I have a chemical reaction. That's why when you're doing this, don't say in your observation, chemical reaction, because that's not the observation. The observation is what you are seeing, hearing, feeling, or smelling. Not so much taste, guys. Okay? I've already been through this. Okay. Allie, have you ever been dumped for somebody else? No, better yet. Allie, have you ever dumped somebody?
Sure.
You have? You left him for roadkill, right?
Sure.
You took that bus and you ran over him. You not only ran him over, but you put it in reverse, right? This
Sure.
poor guy is crying his eyes out on the side of the road, right?
Yep.
But you had something better.
I sure
Right?
did.
Absolutely. So what happened is we had a new couple and we had some poor schmuck that's over on the side of the road crying his eyes out, right? Let's think of it like the Flintstones. Betty's clubbing with Barney and she sees Fred at the bar. Betty starts to think, why am I with this chump when I can be with that guy? So what happens is Betty hooks up with Fred and Barney goes by the wayside. Guys, chemicals are just the same as people are. Anions look over, they see a metal and they think, I can be with that metal and I'll be happier. So they dump the first metal that they're with, and so they hook up with the neutral metal. Single replacement reactions. First of all, you got to recognize them. If you have a metal, a neutral metal plus an ionic compound as the reactants, that is indication of a single replacement reaction. You got to look at the reactants. Metal, ionic compound, you have a single replacement reaction. If the reaction proceeds, the neutral metal is going to replace the cation in the ionic compound, and the cation is going to become ionic. Give you an example. If I throw aluminum, if I throw a bunch of aluminum foil into a vat of silver nitrate, the aluminum, the nitrate is looking over and thinking, I'd rather be with aluminum. So the nitrate grabs hold of the aluminum and they stick together as a new pair. The silver, it's got nobody to be with. So it's neutralized and it is over by itself as a neutral metal. First rule, guys, when we're dealing with ionic compounds, The first rule is the more active element ends up being ionic. That means if the reaction proceeded, the neutral metal displaced the cation, and when it displaces a cation, it becomes ionic. If that happens, then the reaction worked and the neutral metal displaced the cation. The cation then becomes neutral. If the reaction did not proceed, that means nothing happened. If nothing happened, the cation was not displaced. The cation is still got the charge. Does that kind of make sense to you? Let me see if I can give it to you with a better example. I'm sorry for the people in my lecture, but this is the same example I used earlier. Let's see who's out there. Andrew. Andrew, have I embarrassed you recently?
Not today.
Not today yet. Okay. Andrew, I'm a drug lord. I have this big cocaine plantation down in Colombia. Okay. And if I have this big plantation in Colombia, then I need to take my cocaine to Miami, right? Isn't that where all good cocaine goes?
Yeah.
All right. So, Andrew, I have this thing of this kilo of cocaine. You're with me. You're my flunky. I'm looking and I see up ahead, I see Mr. Customs Man. What is the likelihood I'm going to hand that cocaine to you and make you take it through the customs? What is that likelihood, Andrew?
Really strong.
Really, I can almost guarantee it, Andrew. So literally speaking, I got more power. I'm going to give you my cocaine so you can walk it through the customs. Same thing happens with chemicals. If I'm more active, if I'm a more active metal, then what's going to happen is I'm going to force my electrons onto the metal that's the cation. When that happens, I become ionic, and the cation that's taken my electrons is now neutral. So if I'm more active, I'm going to end up being ionic. All right. Let's think of it the other way, Andrew. You're bigger than me. I can see that. All right. You're much more powerful than me. And you know, hey, if I get caught by customs, I'm going to go into prison and I'm going to meet up with Bubba, who is going to be real friendly with me. Okay. So do I really, really, really want to take this cocaine from him?
No.
No. You're going to beat the snot out of me, aren't you, Andrew? Right?
Yep.
And you're going to walk through and you're going to say, okay, I'm good. So in this instance, the cation is stronger than the metal. So the cation gets to stay ionic. Bottom line, the more active metal will end up ionic. Whether that's through a reaction happening because it's more active and it displaces the cation, or if it begins as a cation, no reaction is going to take place because it's more powerful than the metal that's trying to give it electrons. Does that kind of make sense, guys?
Yeah.
Okay. Now, if a reaction goes forward, the reverse reaction will not go forward. What I mean by that, okay, if I put sodium with aluminum chloride, sodium is more active than aluminum chloride. So if I put sodium metal in there, is sodium, because it's more active, Is it going to be end up being ionic? Sodium's more active, guys. Is it going to end up being ionic?
Yes.
Yes.
So the reaction proceeded. Okay, sodium became sodium plus. It became ionic because it's more active than aluminum is. Now, my statement by if the forward reaction goes, the reverse will not. Look at the products of the first reaction. Products are salt, table salt, sodium chloride, and aluminum. If I put those things together, I get no reaction. I get no reaction because sodium is more active than the aluminum, and it's already ionic. So looking at that, I get no reaction. The aluminum could not displace the sodium because it's weaker than aluminum. Okay, so by those two reactions, I know that sodium is more active than aluminum is. All right. Now, I stick gold metal in a solution with aluminum chloride. I get no reaction. Michael, let's see if we've been paying attention. I put a gold in with aluminum chloride and I get no reaction. What is more active, gold or aluminum?
Gold.
Michael, did I get a reaction?
No.
So if I got no reaction, the aluminum chloride stays the same and the gold stays the same, right, Michael?
Correct.
Which one is ionic?
The aluminum.
So remember what I said. The more active metal will end up being ionic. The aluminum stayed ionic because it is more active than the gold is. Does that make sense, Michael?
Yeah.
So right now I know that aluminum, because when gold was mixed with aluminum chloride and didn't react, I know that aluminum is more active than gold is. Am I confusing anybody yet? Okay, let's go on. Now, I react sodium with gold chloride and I get a reaction. What is more active, sodium or gold, Allie?
Sodium.
I got a reaction. I produced Na+. The sodium ended up being ionic, so sodium has more power than aluminum. I got to see more people than what are here. Nathaniel. Nathaniel? Oh, do I take roll now and everybody that doesn't answer? Is Nathaniel in the chat room?
Yes,
Okay.
sorry, I'm here.
Thank you, Nathaniel.
Hi.
So, how was that little snack you just had, Nathaniel?
So I'm actually cooking dinner at the same time.
So's
So my hands
Christina.
were totally covered in garlic. My bad.
Being covered in garlic is always forgivable.
It's not the worst thing possible.
Okay, you've been kind of paying attention, Nathaniel?
Kind of paying attention. I'm trying here.
Okay. I mix neutral iron with aluminum chloride. I get no
Okay.
reaction.
Yes.
Okay, I get no reaction. Does that mean that iron and aluminum chloride didn't change?
Yeah.
All right. What ended up ionic? The iron or the aluminum?
Okay, I think it's the iron, I think.
No reaction, Nathaniel.
Oh, yeah.
There's no reaction. So did the iron change into anything?
No.
It stayed neutral, right? Is it ionic?
No.
So which one ended up ionic? The iron
So
or the aluminum?
chloride. Yeah.
So which one is more active?
Wouldn't it be the aluminum chloride then?
Not the aluminum chloride. We're not saying the chloride. The chloride has nothing to do with it. We're comparing aluminum with iron.
Oh, the aluminum.
The aluminum does.
Okay.
Make sense?
Yeah.
Let's see who else I can bother. Bother Michael. Sheridan. Sheridan, you out there?
Yes, hello.
Hi, Sheridan. How you doing?
I'm good, doing good.
You been paying attention?
Hope so.
Okay, now Sheridan, I put iron in with gold chloride. Gold is ionic, iron is neutral. I do that, I get a reaction. Which one ended up ionic, the gold or the iron?
The iron?
Good. So which one is more active?
The iron would be more active.
Okay, guys, most people get the idea. If they get a reaction, they can see that the neutral metal is more active. The problem you have is wrapping your head around when the reaction doesn't happen. If the reaction doesn't happen, then the cation is more active than the neutral metal. We got a whole lot of data here, guys. We have a whole lot of data. Just looking at this page, can you tell me what is the weakest? What is the thing that has the least activity?
Gold.
Why? Why, Allie?
It's one of the weakest metals. It's all the way to the right on the
Yeah,
activity.
turn that around. Guys, take your activity series, turn them upside down on your desk right now. I want you to just look at this, Allie. Just look at the screen that you see in front of you.
Mm-hmm.
What is the weakest thing?
You mean the whole compound or just the
No,
single?
I'm saying between, you're comparing sodium, gold, aluminum, and iron. What's the weakest one?
Gold.
Why?
Or,
You're right. Don't look at that one. Do not look at that. Look at the screen.
No, I was just making sure my AU is the weakest one.
Well,
Yeah,
no, I
gold.
see, Allie, I don't want you to look there. I want you to look at the information that's on the screen.
Mm-hmm.
Okay?
Well, it's getting replaced in each of the
Well, look.
formulas.
All right, we've made the determination. Sodium is has more activity than gold. Aluminum has more activity than iron, and iron has more activity than gold. What is the weakest one? And give me your logic why.
So the gold is the weakest one because each of these, it's being replaced by the sodium and by the iron.
You're not getting what I'm saying, okay?
Okay.
The logic I would use, gold is less active than sodium. We know that, right? We also know that gold is less active than iron, but iron is less active than the aluminum. So the aluminum has to also be more active than the gold. Does that make sense to you?
Mm-hmm.
Let me see if I can get. Okay. Our first reaction, we had sodium more active than aluminum. And the next one, aluminum was more active than gold. Okay. Now, can somebody tell me what the most active of my four elements is? Sodium is more active than aluminum. Aluminum is more active than gold. And we go over here. Sodium is also more active than gold. And it's more active than, remember, sodium. Let me put this in here. Damn it. I have those four things. Now, can you tell me What is the most active?
Sodium,
Why?
it's more active than aluminum, which is more active than the rest. Apart from sodium.
Okay, I can buy that. Sodium is more active than aluminum, and aluminum is more active than iron. So I
Active.
know, and sodium is more active than aluminum than gold. So sodium must be more active than iron and aluminum and gold. So sodium is the most active. Now, what is the most active between aluminum and iron?
Aluminum.
Why?
It says it's more active than iron.
Because it says it's more active than iron. Because we deduced. Actually, the reason is because when we mixed neutral metal with aluminum chloride, we didn't get a reaction. So if I'm going to go ahead and make my own activity series, I'm going to use all the information I just got. Oh, that's why it's not doing it. I'm not in a slideshow. If I'm going to do my activity series with iron, aluminum, gold, and sodium, we decided that sodium was the most active, aluminum was next, then iron, then gold. So riddle me this. Mariah, you're out there, Mariah.
Yeah.
Riddle me this. We have just made our activity series. Sodium is more active than aluminum, which is more active than iron, which is more active than gold. Knowing that, should gold metal react with sodium chloride?
No,
Why not?
because sodium is more active than the gold.
And it's going to end up ionic. If it's already ionic, then it's not going to react with gold. Now, Allie, you can turn over your activity sheet again. Now, you said something earlier. You had all those metals and the one at the very end was gold, right?
Yeah, second to last.
So what's the last one?
I don't have it memorized. PT.
Platinums? Okay, I could buy that. All right. Do you see that gold doesn't react? Gold doesn't react. If I have gold metal, it's not going to react. The only thing it's going to react with is possibly platinum.
Mhm.
That's one of the reasons why gold is used as a precious metal. It's one of the reasons why it's used in jewelry and why it lasts. It's kind of the reason why you don't have to worry if you're going in swimming that something's going to attack the gold in the pool. You wouldn't do the same thing if you had an iron ring or a copper ring. Anyway, that's just a sidelight.
Question, it's a little off topic. If platinum's less reactive than gold, then why do they use platinum in catalytic converters to break up gases?
Why do they use?
Platinum in catalytic converters then?
Because they don't want it to break down.
But
It's
does that
at that
react
point,
with the gases
okay,
then?
what's it reacting with? It's reacting with a gas, right?
Yeah.
Okay, if it's reacting with the gas, it's actually serving as the electrode in the battery.
Okay.
And so basically what happens is you can't use gas as an electrode. There's just nothing solid there. So you have to use something that acts as, that will be the electrode, and the gas just hits it instead of itself acting as an electrode. That's the reason. The reason they use platinum is because they don't want it to decompose.
Okay, that makes sense.
Okay. All right, now you have two metals. You have tin and calcium. You have tin and calcium. And I want you to develop an experiment, determine which one is more active. What have we been doing? How did we determine that sodium was more active than gold?
Because it didn't react.
What did we do though? What did we put together? I'm talking sodium and gold. What did we do to determine that sodium was more active than gold? What did we put together?
The sodium becomes an ionic compound.
But what did we put together, Christina? What did we physically bring into contact with one another?
Sodium and chlorine.
Not sodium and chlorine,
A metal and non-metal?
not the metal and non-metal,
The two metals.
the metal and the cation.
Okay.
Do you see? What,
Okay, yeah.
if we're going to determine whether sodium is more active than gold, what we're going to do is we're going to put sodium metal in with gold chloride, sodium with the gold ion. If I get a reaction, that means that sodium is more active than gold. I could also do it in reverse. I can put gold metal in with sodium chloride. But when I put gold metal in with sodium chloride, I don't get a reaction. I can develop that experiment one of two ways. I can either make gold metal with sodium ion, or I can make sodium metal with gold ion. So how am I going to distinguish whether tin or calcium is more active? I can't hear you, Christina.
Put them together.
Put what
Mix them
together?
together.
Put what
The-
together?
The metal and the
Tell me
cation.
specifically.
The sodium and the, oh, which one? The first one? Tin
I
and
want
calcium?
to know tin and calcium.
You would
how
mix
am
them
I-
together,
Mix what together?
the tin and the calcium.
If I put tin and calcium together, they're both metals, they're not going to do anything. I want you to be specific, Christina.
Oh geez, I don't know. I'm pretty burnt right now from chemistry, to be honest. Mm,
What do we do? How do we determine sodium and gold? What do we do for sodium and gold? You're just like this close.
Yeah. I don't know.
Allie, you got an answer for me?
We had chloride.
Not chloride.
Well, chlorine.
Nope. Chlorine's doing nothing. We got.
But it's our mixing agent.
I'm sorry? It's
Like
a
we were-
spectator ion. Chlorine is a spectator ion. Nothing happens with the chlorine. What did we do? What did I say we did? Didn't I tell you we put sodium metal with gold ion? Or we put gold metal with sodium ion? Does that make sense, guys? Now you got to make the jump. You have two metals. How do you determine which one is more active? You don't mix just tin with calcium. You mix tin metal with what form of calcium?
Calcium ion.
Calcium ion. So we're going to mix tin with calcium chloride. If we get no reaction, I'm sorry, we mix sodium with calcium chloride. Never mind. Sorry. I can see why you're confused now. Sorry. Stop. What are you doing? Thank you. I can see why you're confused. Sorry, my fault. Bad slide. All right. What I'm going to do is I'm going to take tin metal and mix it with calcium chloride. If I get no reaction, I'm sorry. We're erasing that. I'm going to mix tin metal with calcium ion. There's no reaction. If I had a reaction proceed, If I had a reaction proceed, what would be the ion? I'm not getting this. I'm losing you. I know I am. Let me back up here, guys. Okay. I mix tin with calcium chloride. I get a reaction. Okay. What is the cation now?
Tin chloride.
Tin
Tin?
chloride.
What's the more active metal then?
Tin.
The tin.
Okay. Now, I get no reaction. What is the cation?
Calcium.
What is the more active?
Calcium.
Are you seeing that? Now, I have a way of checking this. I have a way of double checking to see if I'm right. I mixed tin metal with calcium chloride. Couldn't I just as easily go with calcium metal with tin chloride? Does that make sense to you? Either way, I can determine what the more active one is. Okay, so bottom line, all right, we're going to mix a metal with a ionic compound. If a reaction occurs, if there are observations that indicate that a reaction occurs, then the metal is now ionic. It is more active. If no reaction, if there's no visible change, then the cation that was originally there stayed the cation, and the cation will be more active. We add up all of these groups of reactions, and what happens is we look at all of them, we determine an activity series. I'm going to be quiet now and wait for your questions. Are you totally lost, or are we okay? Marie, Mariah, Nathaniel, are we
I'm
doing
okay.
okay, guys?
I'm good.
I'm hearing crickets out there. Mila, are you okay with this?
Yes.
Does it make sense, Mila?
Yes.
Okay. Sheridan, we good?
Yes.
Kaylin?
Yes.
Okay, you're good with it?
Yeah.
All right. Second reaction we're dealing with is a double replacement reaction. Cute kitty, Kaylin.
Thank you. She's a nuisance.
I can see that. Does she sleep in your bed as well?
Oh yeah, all three of them. There's no room for me.
When I had a cat, that cat was right next to me. She couldn't stand my wife because my wife thrashes around in bed. I'm just there as a lump. Anyway, Kaylin, we have a double replacement reaction.
Okay.
What happens to recognize it? When we have two ionic compounds as the reactants, that means in your mind that we get a switching. The reaction is that the cation of the first compound reacts with the anion of the second. The cation of the second reacts with the anion of the first. We have an example here. We have barium chloride plus silver nitrate. Again, barium's a metal, so I know that my first compound is ionic. Silver's a metal. It's also ionic. So I know I have two ionic compounds. So the barium hooks up with the nitrate to make barium nitrate. The silver, the second cation, reacts with the anion of the first. We get silver chloride. Let's think about this. Has anybody ever heard of a key party? And if you're in my lecture, you're not allowed to answer. Allie, have you ever heard what a key party is? Michael,
No.
Nathaniel. Anybody know? This is a thing. I grew up in the 70s, guys. This was big in the 70s. What happens at a key party? The couples go into a house. The man throws his keys into his big jar. And the woman gets blindfolded and she reaches in, grabs a set of keys, and she hooks up with whatever man those set of keys go with. If we're talking about the Flintstones, Fred and Wilma meet up with Barney and Betty. They switch off. Fred ends up with Betty. Barney ends up with Wilma. We start up with two new couples. That's what happens in a double replacement reaction. So what we have to realize is that the reaction proceeds if we can notice a change. Sometimes what you'll notice, most of the time when we're dealing with these things, you're going to see a solid forming. What happens is the solid material doesn't dissolve in water, so it solidifies out. We have a new chemical property. We observe that the solid material doesn't dissolve anymore. It solidifies out. New property, we probably have a reaction. Also, if you get a change in color, that could indicate a change. Or if you get bubbles happening, that could indicate a change. Now, we need to talk about ionic equations because that's what a lot of this particular exercise is going to involve. If an ionic compound is soluble in water, it exists as ions. I take salt, I put it in water. Salt no longer exists as the compound sodium chloride. It exists as separate ions, sodium and chloride. They separate into the cation and the anion. Now, to describe what happens, you need the number. What you do to get the number of ions, you multiply of the balanced chemical equation, you multiply the coefficient times the subscript of that element. That will give you the number of ions that are formed. You follow that with the elemental symbol. Each one needs a charge, and then you got to put aqueous down below. You need four things to describe an ion: number, elemental symbol, charge, and the fact that it's either aqueous or solid. If I'm dealing with 4 sodium sulfates, I multiply the 4 by the 2. I know I have 8 sodium ions. Sodiums have a +1 charge, and because the whole compound has this AQ, I know they're aqueous. So I define it as 8 Na1+ aqueous. Mila, how many sulfates do I have here?
4.
No,
Oh, 16.
no.
1.
I'm sorry. 1.
There's
Yeah.
1 sulfate in each. Okay.
I'm sorry. They're so wild today.
Just mute it, Mila, and I'll explain it to you, okay? There are no parentheses. Remember, in order to have a sulfate, I need 1 sulfur and 4 oxygens. So there are no parentheses, so I know there are 1 in each compound, but I have 4 compounds because the coefficient is 4. So 4 times 1, this means I have 4 sulfate ions. Each one has a 2- charge, and they are aqueous. If a compound is designated as S, it is a solid and it stays together. So I have this balanced chemical reaction. 3 BaCl2 aqueous plus 1 Ni2SO4 aqueous yields 2 NiCl3 aqueous plus 3 BaSO4 solids. Kaylin, how many
Yes.
barium ions do we have?
3.
What's the charge on barium?
-1. Is
No.
it? Barium +2.
+2. Good go.
Yeah.
How'd you go from -1 to +2?
I think I was thinking of bromine.
Okay.
The other B one, you know.
The other B1. All right. Okay, so to describe the barium ion here, I'm going to say 3 Ba2+ aqueous. How about the chloride, Kaylin?
6. The whole thing.
The whole
6
thing.
Cl +2. Is that
Cl,
right?
what's the
+1?
charge on Cl?
See, that time I was thinking of calcium. I can't get them right. Cl's -1 and then AQ.
Okay, so if I'm splitting up this compound, I have 3 Ba2+ aqueous plus 6 Cl- aqueous. See who else I can bother. Lewis, you out there, Lewis?
Yes, sir.
Okay, Lewis, are you understanding what we're doing to break this up?
A little bit, yeah.
Okay, so let's see if we can work our way through it, Lewis. How many nickels do we have there?
2.
2. So I got 2. What's the symbol? It's right here, Lewis.
Ni.
2 Ni. Now we got to figure out the charge. Okay? We have to use the anion to determine the charge. Do you know what the charge on SO4 is, Lewis?
SO4 is -2.
-2, but I have 3 of them, right?
Yeah.
So if I have 3 of them, that means the total negative charge is -6.
Okay.
That's balanced by a total positive charge of
+6.
+6, but it's distributed to how many nickels?
2.
So I divide the 6 by 2. What's the charge on the nickel?
3.
3 plus. So putting it all together, 2 Ni, 3 plus aqueous. Okay?
Okay.
Now, Lewis, how many sulfates do we have?
Well, 4 and then
Nope. The 4 is part of the ion, Lewis.
so 3.
3. Whenever you have parentheses, and I ask you how many there are, it's the subscript you're going for.
Okay.
I got 3 times the coefficient 1. I have 3 SO4s. What's the charge, Lewis?
All together -6.
Nope, no, I don't want all together. I want each. At this point, I want the
Just -2.
-2. So I've got 3 SO4, 2 minus aqueous. Okay?
So that's just in parentheses for the SO4.
Yes.
Okay.
The only way, Lewis, you have more when you have a polyatomic ion. Okay? The only way you have more than one of them is if you have parentheses. If you have no parentheses, there's only one of them. Like, for example, over here, Lewis,
Right.
You see the SO4? There's only one SO4 there.
Okay.
Make sense?
Yes, sir.
I'm here to answer questions. Let's see. Malin. Malin? Somebody dropped out. Somebody's tired. Jordan. I know it's not Jordan. I know it's something else. Jordan. It is Jordan.
Yeah.
Jordan, we're going to do the next compound. It's aqueous, so it breaks up. How many NIs do I have?
1
What's the coefficient, Jordan?
of 2.
So remember, when you're doing the number of the ions, you multiply the coefficient by the subscript. So there are how many NIs?
2.
Okay, now this nickel has a charge of what? If each chlorine's a -1, Jordan, what's the
Alright.
total negative charge?
-3.
So what does that make the charge on the nickel?
-3.
+3. It has to balance it.
Positive. Yeah.
So I designate my nickel as 2Ni 3+. How many chlorines do we have, Lewis? Or Jordan?
6.
6 Cl. What did we say the charge on the Cl was?
-1.
-1, aqueous. Now, save us some time, guys. What do we do with the BaSO4?
Nothing.
Nothing. We leave it alone. It's a solid. So to summarize, if I want to get all my ions, this is the total ionic equation. All right. Now, to go from the total ionic to the net ionic, I got to cancel out what's the same. What's the same, left and right? Anybody?
The 6Cl and
Nickel.
2Ni.
6Cl is the same on both sides, so I'm going to cancel that. Sorry. I'm going to cancel that and my 2 NIs. When I cancel everything on left and right of the arrow that's the same, I am left with the net ionic equation. The net ionic equation is what is really happening in the equation. The Ni3+, it's not doing anything. It's staying the same. My 6Cls, they're not doing anything. They're staying the same. But what is happening is I'm getting 3 Ba2+ reacting with 3 SO4 2- to make 3 BaSO4s. Are we good with this, guys? Kind of good?
Yep.
All right. I'll give you the option. I've been talking for about an hour now. Are we good enough that we don't need to go through another example of this? Remember, I can do the same thing with a single replacement reaction. If I do the ionic, if I split everything into ions, I get this whole thing. What's the same in an ionic equation are the anions. They cancel out, and I'm left with this. And that actually is all that's happening in a single replacement reaction. I'm getting electrons to transfer from one metal to the other. Okay, oh God. All right, now, are we good, guys? Are we fairly solid on the theory now? I know I've been boring you for about an hour now. My voice is about shot. I got to go through the report itself. All right. What it's going to ask you. It's going to ask you 5 questions. There are a series of reactions that you're going to have to. You have to look at the video. And the video, I think, is about 23 minutes long. You're going to look at the video and he's going to describe what's happening as you see it. All right. The first question you're going to get asked for each reaction is, did the reaction go? Then you're going to get the neutral metal, cation. That is the neutral element that you are reacting, the things before you mix them. The neutral metal before you mix it, and the cation of the ionic compound before you mix it. Then you're going to mix it, and you're going to determine whether the reaction goes or not. And then depending upon whether the reaction goes or not, you're going to have to identify the more active metal and the less active metal. That's how, for each question, you're going to have 5 questions. Did the reaction go? Neutral metal before mixing, cation before mixing, most active, least active. And I will show it to you so you're not blindsided by it. You added aluminum metal. Aluminum metal is shiny. You added it to a blue solution of copper nitrate. What happened is the copper nitrate solution's blue. After you mixed them, the copper solution faded and you got a brown solid forming. Did you have a reaction?
Yes,
Why?
because a brown solid formed.
Brown solid
Saw
formed?
it.
There are 2 observations. The brown solid formed
Mhm.
and the blue
The
color faded.
copper, yes,
You were forming copper. Where'd the copper come from, Allie?
from our compound.
From the copper nitrate solution. Remember,
Yes.
the copper nitrate solution is what's making the solution blue. If you're taking the copper, it has to come from somewhere. It comes from the solution, so that blue color fades. Okay, so overall reaction, I mixed aluminum with copper nitrate. I got a reaction, so aluminum formed, aluminum nitrate formed, and copper metal formed. Okay, so I got a reaction. The answer in the report, yes. Aluminum was the metal, was the neutral metal I added. Cu+2 was the cation. Since the reaction went, the aluminum ended up being ionic. So aluminum's the more active, copper is the least active. That is like the first 8 questions of the results section of the report. Are we good with that? Do we understand what's being asked of you?
Yes.
Is that it? Is that the last slide? No, there's got to be more. Okay. I'm going to stop the slideshow at this point, and I'm going to get to the, if I can find, yeah, there it is. I'm going to get to the actual report, guys. Okay. Report, good. Review. And start quiz. Ouch. Ah. I got to move this thing. Okay. Like I said. All right. You're going to be able to print out the lab report, the lab manual, and you're going to mix, or Dr. Musgrave's going to mix magnesium and HCl. You're going to determine whether a reaction happened or not. So after you determine whether a reaction happened or not, you're going to be able to complete the chemical reaction. If no reaction happened, all you got to do is put NR. That means no reaction. Okay. Now, these are my reactants. You mixed magnesium and HCl. So the neutral metal is going to be, don't answer that. It's going to be one of these two things. The cation is going to be the other thing. Okay. Now, if it reacted, then the magnesium replaced the HCl, and the magnesium is going to be more active. You list that first. If it is less active, you list that second. Any questions on how to fill out these type of questions here? Again, that's what the first, all these questions are. And notice there, he loves giving you like 16 choices. Be careful. Be careful when you read them because he likes to be tricky. He might do something like, say, instead of Cu plus 2, he might put a 1 plus there. So read the question, read the answers carefully. Okay. All right. Next thing. This is the one from 8 down. You have to be very, very careful because he futzes with the subscripts. Be very, very careful when you're looking at this. Okay. You have a choice. If no reaction, all you got to do is pick out the no reaction part. Okay. If you did say there was a reaction, you got to give me, you have to give me the balanced products. The overall reaction will not be balanced, but the products have to be balanced. So what's the charge on Mg, guys?
+2.
+2. How, if the reaction goes, how many chlorines are you going to put with it?
2.
There we go, Christina. So I'm going to say one of my products is going to be MgCl2. The neutral thing is what then?
Hydrogen.
Hydrogen. Now, how does hydrogen exist in the real world?
Diatomically.
Diatomic. So you can't say this answer is wrong because the hydrogen is not listed as a diatomic. That is the correct one. And keep in mind that he also switches these around. Are you kind of understanding what I'm meaning by be careful about the subscripts, guys?
Yes.
All right, that is, again, you're going to go through all those same ones. All right, based upon all these reactions, you're going to have copper, you're going to have copper, zinc, magnesium, and hydrogen. Based upon those reactions that you did, you're going to have to determine which one was the most active, just like I did with my little example, okay? You're going to have to determine which one's the most active, which one is the least active. Then, of the other two metals, you're going to have to say which one of those two that are left is the more active. So you now can create your own mini activity series. And be careful about this. Make sure that you know when you're listing these elements, the most active is number 1. Least active is number 4, because I see it all the time. I go through and I'm checking these. I see that you've done the exact opposite. So it's kind of like, I know you know what the right answer is, but you're not reading the question correctly. Now, this question is going to be about kind of that last question I asked you about whether calcium or tin. How would you design an experiment to determine whether calcium or tin is more active? Remember, you're taking the metal of one mixing it with the ionic compound of the other. Okay, then you're going to have to do, you have two double replacement reactions. You're going to see, again, this one is tricky. You're going to mix lead nitrate and potassium iodide. By the way, ladies and gentlemen, be awful happy that you are not doing this experiment. Lead nitrate is very toxic. So notice you have very, very similar descriptions, right? White gel-like, white powdery, yellow. Okay. You're getting very, very similar. So be very specific about how you're observing this. Okay. Again, you have to be very careful about this because he putzes around with the subscripts. So he's asking you, split up these two compounds so that you have the ionic ions on the left side. There are two ionic compounds. They're both aqueous. So you're going to have 4 answers there. Again, be careful because he has some funky answers in there. Make sure your description is exactly correct. Like, when you look at this compound, is there a subscript 2 there? So how can it possibly be I2 2 minus? Okay, be careful about that. This question you're going to have 4 answers to. Next question. Okay. Thank you. Thank me for going through this. I have to explain something. All right. There is a concept called sum of the coefficients. And basically, sum of the coefficients is nothing more than an easy way for teachers to ask questions. Okay. A teacher can tell you, balance this chemical equation. And in order for him to determine whether you balanced it correctly, all he does is tell you, add up all the coefficients in front of all the compounds that you have listed. Say, this is going to make lead iodide and potassium nitrate. Say there was a 2 coefficient in front of the lead, no number in front of the Ki, there was a 3 in front of the Pi, and there was a 4 in front of the KNO3. So I have 2 plus 1, 3, plus 3 plus 4. 3 plus 3 is 6, plus another 4, 10. I add all the coefficients in front of these all up. That is what the sum of the coefficients is. Remember, if there's no number in front of a compound, it still has an assumed 1. Okay, this question, you're going to have to give me 2 answers. You're going to have to give me 2 answers. You're going to tell me, predict what compound A is and what compound B is. And again, notice he futzes with the subscripts. Got to give me the exact subscript there. Okay. Now, you have to take this equation. For this one, he's asking you the full ionic equation. You have to break it up into all of its ions. Then whatever coefficient is in front of the ion, you have to add up each one of those. And that will give you the sum of the coefficients. Then you do the net ionic equation, same thing. Then you're going to go through the second one, all of those same questions. Do you have any I'm sorry, let me go through and see the very end of here because I think there's something else at the very end. Okay, there are 3 questions at the very end. I'm sorry. All right. You have a solubility chart. There's a solubility chart in the lab. Okay? You have to figure out what your products are with lead nitrate and magnesium sulfate. You have to figure out what the products are. Then you have to use the solubility chart to determine if one of them is a precipitate, if one of them is a solid. If neither one is a solid, it's no reaction. If there is a solid form, you have to tell me what the products are. And there are 3 of these. Is anybody not familiar with the solubility chart at this point? I'll be happy to stay afterwards, but I think you're pretty well tired by this point, especially those of you that just got done taking my test. Do I have any questions, ladies and gentlemen? I'll be happy to go through the solubility chart. Stick around after everybody leaves. I'll be happy to go over one with you. That's all I got for you. Are we good? Are we kind of confused? Are we okay? Ellie, Ellie, I know you're good. Christina, I know you're good.
Have a good
Okay.
spring break.
Yeah, I'm going to be having an operation over spring break. Woohoo!
Oh, geez. Well, I hope you recover well.
I'll be fine.
Good luck, soldier.
All right, good.
I'll be fine. I'll be absolutely fine. No problem at all. Actually, I'm planning on going into my lab 2 days later. My wife may be wheeling me in a wheelchair, but I'm planning on going. She doesn't know that yet.
I bet she'll love that.
Yeah, well, she's made me suffer through Haydn's Messiah. Has anybody ever watched the Messiah all the way through? God bless you if you have, because it's the most boring piece of music I've ever heard in my life. The Hallelujah chorus is, the words are, will this ever end? Hallelujah, hallelujah. Okay, guys, take care.
Thank you. Have a nice spring break and a safe surgery. See
Thank you very much. You guys take care. Don't worry about it. I'm going to be fine.
Take care. Thank you.
Take care. If you have questions, stick around. I can answer them.
Take care.
Take care.